Good afternoon, everyone. Today I would like to share my research result with the title of Estimation of Restaurant Expansion and Shrinkage Strain of Reinforced Expansive Concrete. So this is the outline of my presentation today. First, introduction. Second, scope of the study. Third, methodology. It's including experimental and finite element analysis. Fourth, about results and discussion. And the last one is about conclusion. So start with the introduction. As we know, concrete has several disadvantages such as time-dependent volume reduction, such as drying shrinkage, thermal shrinkage, autogeneous shrinkage, and carbonation shrinkage. In addition, concrete also has a low tensile strength capacity. So because of these two drawbacks, crack can occur due to the low tensile strength capacity and high shrinkage. When the elastic tensile strength reach the tensile strength capacity, so the concrete will start to crack. So this is some example that crack occur on concrete. So one of the method to prevent shrinkage cracking, we can use expansive concrete. Actually, expansive concrete is not much different compared to normal concrete. We just need to add the expansive admixture at the mixed proportion, and then after we mix together, it will be expansive cement paste, and then after setting time, the volume will be increased. So in this figure, it show the comparison of expansion and shrinkage between normal concrete and expansive concrete. In expansive concrete, the volume will be expand uh, during the curing period, and then after that start to shrink. But in normal concrete, it's expand but in during the early age, but it's not much as expansive concrete, and then after that start to shrink also. After some time, we can see for example, like around here, actually the tensile strain of expansive concrete is smaller than normal concrete. So that's why based in this concept, we can conclude that expansive concrete can prevent the shrinkage cracking. Uh, Actually, we have already many type of expensive cement or expensive additive. For example, like based on ACI, we have a type K, type M, or type S of expensive cement. However, in this study, we focus only with the expensive additive that commonly used in Thailand. In this study, we focus on CAO type, CASA type, and blended of CASA and CAO types. As I mentioned before, uh, actually we have already the design standard of expensive concrete such as SCI 223R10, GSCE number 23, and GISA 6202. However, this standard has some limitation that we cannot apply in uh, some country for especially in Thailand. Some limitation here, the type of expensive additive only CAO based and CSA based. However, in Thailand, as I mentioned before, we also have another type of expensive additive, which is blended CSA and CAO based. Uh, the other limitation is in the standard, it's only focused on water curing, and the curing temperature standard is 20 degrees Celsius for GSCE and 23 degrees Celsius for ACI. However, some condition in Thailand, we utilize the other types of curing such as moist and silk curing, and also for the curing temperature standard is 28 degrees. Also in X16 standard is not include the effect of cement replacement material. However, almost all of the concrete uh, structure in Thailand utilize fly ash as a cement replacement material. So based on this limitation, that we need to improve the design guideline with consideration that happen in Thailand. So this is the scope of my study. In this study, we divide into two level. So level 1, we focus on laboratory tests, and level 2, we focus in the structural monitoring. So in laboratory tests, we varied some mixed proportion, water to binder ratio, curing condition, and reinforcement ratio. And then after that, we try to predict the verify the restraint expansion strain, because in this study mainly we focus on the estimation of length change behavior of expansive concrete. So we start to estimate with the rest in the laboratory scale, and then from this analysis finally we can generate the effective free strain. I will explain later what is effective restraint, and then after that we want to apply this effective restraint to in the structural level, uh, and then we choose some type of structure. Here we have a slab on grade, slab on beam, water tank wall, and slab on pile. After that we verify the result with the structural monitoring. So this is the methodology for the experiment and finite element analysis for prism specimen. So in this experiment, we have actually three type of measurement. First is compressive strength. Second is free strain in the free condition, and then the last one is strain in the restraint condition. So in this part, first we conduct the laboratory test, and then after that we want to evaluate the expansion strain under restraint condition. In this case we use a finite element analysis, and then we try to utilize the free strain as input load. But when we use the uh, free strain as input load, the result always overestimates. So we need to know why the result of a prediction for the expansion strain in expansive concrete always overestimate. So this is the expansion behavior of between free and restraint condition in expansive concrete. So in free condition, the expansive product can expand freely because there's no restraint. Uh, so the volume of pores might not reduce. However, in restraint condition, the expensive product cannot expand freely because the effect of restraint. So some of the expensive product might fill into the pores. So the volume of pores might reduce when we use expansive concrete under restraint condition. Beside that, we also, because of the effect of restraint, compressive creeps also appears. So because we simulate this finite element analysis with the macroscopic level, so we cannot also model the effect of pores into the finite element analysis. So that's why the process the result of estimation of restraint expansion, it's overestimates. In this case, when we use free strain as input in finite element analysis, so the result always overestimate. So we need to find the solution. So we try to find the effective free strain with with application of some reduction factor. However, we still don't have the reduction factor equation here. So in this study, we try to propose the reduction factor equation. So this is the methodology how to propose the reduction factor equation. First, we need to validate the FEM result with the experimental result for normal concrete. So in this result, actually, we can see that without reduction factor, we can simulate the strain behavior of normal concrete under restraint condition. And then after that, uh, with the same method, we try to simulate for the expansive concrete. However, the result, as we can see here, the result of finite element is overestimate than to the experimental results. So after that, we try to reduce the free expansion step by step. In here, we try to reduce like for example here like a 0 0.9, 0 0.8 the constant, and 0.7 to 0.6. And then after that, from here we can see that actually with the reduction 0.7, the result of estimation is matched with the experiments. So in this case, uh, the reduction factor is 0.7. And then we apply this method to all of the specimen. In this analysis, we have more than 150 cases. For each case produce one reduction factor, and then after that we use MATLAB to generate the equation. So this is the reduction factor equation. In this equation, we divide the equation become two part. It's based on the type of curing, as I mentioned before. Like we also consider about the moist curing and seal curing. And then for the component input in this study, we consider about the amount of binder, amount of EA, amount of fly ash, reinforcement ratio, water to binder ratio, and also curing temperature. So in this slide, I already show also the range of the amount, for example, like amount of binder. So this is the amount of binder we use to generate the equation. After that, we need to reanalyze the all of the data with the application of reduction factor from this equation. And then this is the expansion strength comparison between experimental and estimation. As we can see here, with the application of reduction factor equation, the correlation for moist curing is 0.9691. For seal curing is 0.9666. That's mean that they have a high correlation between the result from the test and also result from the prediction. However, we also try to apply the result with the other previous researcher. So in here, we try to apply we try to predict the restaurant expansion strain here with this data, and then we can see that the correlation also high, more than 0.97. And then another research for moist curing, the result also, the correlation also high, 0.95. So from this result, we can conclude that with the we try to apply in other researcher data, then the correlation also high. So this reduction factor to generate effective free strain can be used as input in finite element analysis. So this is an example, the comparison result between a finite element analysis and experimental. So in this result, we can see that finite element analysis can predict precisely with the experiment with the variation of reinforcement ratio, both for moist curing and seal curing. And this with the different amount of EA, the finite element analysis also can predict precisely both for moist curing and seal curing. So after we can predict the restaurant expansion in the laboratory level, we want to apply this reduction factor equation to the structural level. So in this study, we have four type of structure: slab on grade, slab on beam, slab on pile, and water tank wall. However, in this presentation, I only show some example because it's we have some time limitation. So this is the finite element analysis for for full scale structure. We have a slab on grade and also slab on beam. We have also the measurement result both for slab on grade and slab on beam. So this is the result of a damage pattern for normal and expensive concrete for slab on grade. So in slab on grade, in here I choose like two cases. First case of normal concrete, and then second case of expensive concrete. For normal concrete, in the actual structure, uh, after the investigation, we can see that they have a crack at the center of the slab. It's also happened in the finite element analysis results. But in expansive concrete, we can see that in the actual structure there's no crack. It's also similar result with the finite element analysis. So from this result, we can see that actually expansive concrete is sufficient to prevent the shrinkage cracking. This is another example for damage pattern of a normal and expansive concrete for slab on beam. So this is a normal concrete, this is a expensive concrete. We have two different expensive concrete because we use a different type of expensive agent. So but we can see that in normal concrete, the damage pattern, the crack, it's more than crack in the expensive concrete. So based on this result, we can conclude that expensive concrete sufficient to prevent the shrinkage cracking. So this is some example for the comparison between finite element analysis to actual structure investigation. So in here for slab on grade, actually we measure at the center of the slab and also at the edge of the slab. In here we have a three slab. We have SG1 is for normal concrete, and then we have SG2 and SG3. Actually SG2 and SG3 is expensive concrete, but we use a different amount of EA. From here we can see that expensive concrete, both for SG2 and SG3, produce higher expansion compared to normal concrete. And also we can see that the application of reduction factor to predict the restraint expansion and shrinkage strength, it's sufficient compared to the experimental results. And then this is the other sample for effectiveness of expansive concrete for slab on beam. We measure into location. Here it's a near transfer perimeter beam and between two adjacent footing. In this analysis also we have three slab. First slab is normal concrete, the red line, and then after that we have SB2 and SB3 is expensive concrete, but we use different amount of EA and also different type of EA. In here we can see that expensive concrete is expand in the early age, and then after that start to shrink, and then the result of finite element analysis is matched compared to the field investigation, both in the two measured location. So based on the results and discussion, we have some conclusion. First, the reduction factor used to determine the effective phase strain can be effectively used to estimate the restraint expansion strain in expensive concrete structures. The observed crack pattern indicate that expensive concrete effectively prevent the shrinkage cracking, as evident by the field investigation and finite element analysis. So the equation of reduction factor takes into account several factors, including the binder content, expensive additive dosage, fly ash content, water to binder ratio, reinforcement ratio, curing temperature, and type of curing. So that's all for my presentation today. Thank you for your attention.